Hello! In this video we will solve a couple of problems that are not practical to solve by hand, so instead we will use Excel. You may also use R for some of those problems. Okay, say that we are given a random variable from a multivariate normal distribution that has 5 elements, and that we are given the mean vector and our covariance matrix, and that we want to find the conditional distribution of x1 given x2, where x1 is this partition, so x1, x2, and x2 is this partition, x3, x4, x5. What we actually want to use here in order to find this distribution is our theorem number 5. So that theorem tells us that if this is a positive definite matrix, or if its determinant is larger than 0, then we can find the distribution of this vector, and it is given by a formula, let's say, where we have a mean vector and also our covariance matrix for this distribution. So it will have a normal distribution. What we know is that the dimension of this vector, so we have a dimension of 2, dimension of 3, and dimension of 5 for each of these vectors. So the distribution of this one by the theorem is going to be the same dimension as this vector. So we will have a vector that has a bivariate normal distribution with particular mean and covariance matrix. But first, let's check if the determinant of the matrix is larger than 0. Okay, so we know that it is larger than 0, so we have all assumptions from our theorem. So now what we need to determine the distribution of this vector are our mean vectors, so μ1, also sigma 1, 2, then inverse of sigma 2, 2, as well as sigma 2, 1, but it is just similar to sigma 1, 2. Okay, so first we know that sigma 1, 1 is going to be this here. So this one is our sigma 1, 1. Then sigma 1, 2 is this one, sigma 2, 1, and sigma 2, 2. Okay, so we need to make the borders so it looks the same. So 4 borders here and here, just to make it look nice. So what did we say? This is our sigma 1, 1, sigma 1, 2, sigma 2, 1, and sigma 2, 2. Right, so this is our matrices that we need. Okay, so what are we looking for? Will be given here. Let me just move here. So this is what we are looking for. Then we need our μ1. Okay, so μ1 is just the first two. We need μ2, so those three, right? And in the end we need x2, because x2 is equal to x2, so this is our small x. And we can write it as x1, x2, x3, for example, with the borders. Okay, so what we need now is that our vector, so our x2 equal to, it won't look nice. So x1, in condition that x2 is given to x2, has this distribution. So we can just type our, let's say, mu now, and our sigma. So this is going to be a vector of 2 elements, and this is going to be a matrix of 2 elements. Right from here, we know already by the theorem what is the mean vector and the covariance matrix. Okay, so our covariance matrix is, so what do we have? Sigma 1, 1 minus sigma 1, 2. Okay, so we need here matrix multiplication. Sigma 1, 2. Then we need matrix inverse of our sigma 2, 2. Sigma 2, 2 inverse, right? And okay, so we need here one more matrix multiplication of sigma 2, 2 to the power of minus 1 and our sigma 2, 1. Control Shift Enter and we get our matrix. So this is our covariance matrix. Let's put it in order. Okay, to find the mean vector we would need some values, x1, x2, x3, for example, those. So these are for x1, for x2, and for x3, and we would need the difference between those. Okay, so this would be our another vector, and for our mean we would need to take just mu1 minus matrix multiplication sigma 1, 2, then again here we need matrix inverse of sigma 2, 2, then we would need this vector, and that would be it. Yes, but we need to select both of those and find values. So this is going to be our mean for these values. So let's just double check this. We have me1, okay, sigma 1, 2, inverse of sigma 2, 2 times the difference, and we get this one. Let's make it look nice, and this is what we got. So it has bivariate normal distribution with these two parameters, if we are given this part here. Okay. Next problem is simple computation of maximum likelihood estimates. So say that we have this matrix X and that we want to compute the maximum likelihood estimates. So even if we had more data, it would be the same and easy way, but we'll just show it on 2 and very simple of 4 observations. So our mu hat would be the average, so average of each of the columns. So this would be our mu hat, let's say, but transposed. So this is our estimate. To get the estimate, maximum likelihood estimate of the covariance matrix, what we need is the difference. So we need difference between the observed values and the mean, corresponding mean. So let's do it like here, and let it be like this. So what we need is actually this one minus this. So this is our transposed vector. Okay, and our estimate of the covariance matrix, as we did in one of the introductory classes, will be so 1 divided by n times matrix multiplication of, so our estimate would be, as we did previously, 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times matrix multiplication, so we need to transpose this one and multiply it with this one. So 1 over n, so 4 times ma So what we get is our covariance matrix, so our estimate. So this is just simple to show how it works. And the goal of the last exercise is to compute the QQ plot and RQ value. We'll see how and what do they represent. So say that this is actually annual rates of return with dividends multiplied by 100, so that we connect this to finance somehow. To get the QQ plot, what we first need to do is to order these values. So we can just right click and go sort from the smallest to largest. And then we again need those values. Okay, then what we need is to obtain values. So 1 minus 1/2, so we can type 0.5 divided by n, in our case 10. Okay, so what we get here are the numbers. Okay, so actually not 1, but this, because we want to compute for everything at once. Okay, so this is what we get. So those are our probability values. Then we need our quantiles. So from standard normal, so we go normal, inverse to obtain the quantiles. We need to type, because we need standard normal, 0 mean, and standard deviation 1. Okay, so we can check. Okay, so these are our quantiles. And we in the end need those values because we need to plot them. So what we need to plot is this here. Click analysis. And here we can see our QQ plot. We can always remove line or something, but what we need is the trend line. As we can see, it is not that straight from the QQ plot. So these values are our quantiles, and the y-axis would be our values, ordered values, just to mention that. And we cannot conclude that it has a normal distribution. However, our sample is fairly small, so it is only 10 observations. We would need would like at least more than 20, but even more than that to determine using the QQ plot. In the same way, you could compute the chi-square plot. Just take appropriate quantiles and plot whatever you need. We will not make this QQ plot look nice for now. You can if you want to. And we need to compute RQ, so our value. So this is our correlation coefficient test for normality. So we will use the table in the given literature and the value from the table to determine what we need, so to test the hypothesis. So I will pop up somewhere here the correlation coefficient for the test of normality. So what we need is average, right, of our quantiles and average of our values here. Okay, this is expected because the distribution is symmetric. Next, what we need is our sum. So first we need those minus our average. Okay, and we actually have 10 of those values, so go up to 10. Okay, so this is our x yacht minus x. We need again those values. Then we need to multiply them. So this is our x0 minus x times q0 minus q bar, and we need sum, right? I will write above what represents what, so you can see. Then we need squared values, so we need to square this, and we also need to square these values, and in the end to sum them and find square root. So we need square root of sum, and we need square root of sum here. Okay, so we have all the values that we need. Okay, here I think it is a mistake. Yeah, so we need to multiply those, right? And in the end, we can compute RQ as this sum divided by this times this. And we get 0.95. So this is our correlation coefficient. And then we can test the hypothesis of normality at some significant level alpha, it does not matter, depending on the table. In the table we have the sample sizes and significant levels and particular values for the critical points for RQ. So because we have sample size of 10 and say that we want to test at 0.1, let's say, then we will have our critical value to be 0.9351. So this value has been taken from the table. So what we can conclude is, because at, let's say that this is, what did I say, 0.1, right? So because RQ is larger than the critical point, then we cannot reject hypothesis of normality at this significant level. But even though we got this result, we need to be careful because the sample size is small. So you should always need to do more analysis to make a conclusion. Again, this is not practical to do by hand because you cannot compute the quantiles. So you would need a software to compute for each of those values a quantile. Before I send this, I will make it look nice. So this will be it for the Excel. So see ya next time.